So in our last class, I was discussing this on-load operation of transformers connected in parallel, assuming equal voltage ratios. Okay. So all the transformers connected in parallel are having equal voltage ratio or turns ratio. And we have arrived at this equation, that is IAZEA is equal to IBZEB, which means the voltage drop across the leakage impedance of two transformers are same. Okay, therefore we can represent the two transformers connected in parallel by this circuit. That means the previous circuit is modified to this one. Okay, so replacing one voltage source, replacing two voltage sources by one voltage source of equal magnitude, that is EA equals to EB, and applying that voltage across the leakage impedances of the transformers connected in parallel, which is in series with the load. So this is the load impedance and these are the two leakage impedances. Okay, as we know, if two voltage sources, DC voltage sources, if we connect them in parallel, then the voltage appears across this terminal will be equal to the voltage of the source which is having higher magnitude. Suppose this battery is of 10 volt and this one is of 5 volt, so we will get 10 volt here. Okay, if they are equal in magnitude, then we will get the voltage of one of the source. Okay, so here the two voltage sources are having equal magnitude and they are in same phase also, so we will get EA is equal to EB, and we can redraw the circuit using only one source. This I have already discussed in last class. Okay, now applying current divider rule at this point, we can find the value of IA and IB. Okay, that means the load current shared by each transformer. So IA is equal to ZEB. That means while calculating this current, we have to consider this impedance first, then divided by the sum of the two impedances into the total current I. So this is the load current shared by transformer A. Okay, and similarly we can write the load current shared by transformer B, that is IB is equal to ZEA divided by sum of the two impedances into total current I. Is it clear up to this? Any question?
Yes, sir, it is clear.
Now if we multiply these equations by the voltage V, that means the terminal voltage, then we can write these two equations, that is SA is equal to ZEB by sum of the two impedances into S, and SB is equal to ZEA divided by sum of two impedances into S. Now what is this SA? That is the load VA shared by transformer A. SB, that is the load VA shared by transformer B, and S is the total load connected to the system. So VA is the volt ampere load connected to, that means here the product of voltage and load current, voltage across the load impedance and current flowing through the load impedance. This product of voltage and current will give you the total KVA loading to these two transformers, and the load shared by each transformer is given by these equations. This equation. So here SA is equal to ZEB by ZEA plus ZEB into S, and SB equals to this. Okay, so SA is actually the load voltage into the current shared by transformer A, and SB is equal to load voltage into the load current shared by transformer B. Now from 6 and 7 we can conclude that this load sharing is inversely proportional to the leakage impedance of that transformer. How we can conclude like that? Let us consider there are n number of transformers connected in parallel. Okay, so the previous two equations can be modified to this, that is, the terminal voltage is equal to the induced EMF of each transformer, that is induced EMF across the secondary of each transformer minus the leakage impedance drop of that particular transformer. So all these will give you the terminal voltage V. Okay, so this is the terminal voltage of transformer A, this is the terminal voltage of transformer B, in this way up to nth transformer, and that is equal to V, which is the voltage appears across the load impedance Z. So I into Z. Now if all the secondary induced EMFs at no load are equal, that is EA equals to EB equals to EC, as per our assumption, that is equal voltage ratio, this is true. So if we take these secondary EMFs, induced EMFs at no load is equal to E2, then we can write this equation, that is E2 minus V, that is the voltage drop across any across the leakage impedance of any transformer. This is the voltage drop across leakage impedance of transformer A, this is the voltage drop across the leakage impedance of transformer B, and so on. So let us assume that voltage drop equals to small v. So from this equation we can conclude, or we can observe, that with a lower value of full load current, suppose IA, it is the full load current of transformer A. So to have this equal voltage drop across the leakage impedance of each transformer, since this full load current of transformer A is low, therefore this ZEA has to be high. Okay, if IB is greater than IA, that means if IA is greater than IB, in that case ZEA will be less than ZEB. Is it clear?
Yes, sir.
So that the product of IA ZEA is equal to IB ZEB. Okay. So in this way we can conclude that this full load current, the load shared by any transformer is inversely proportional to their leakage impedance, or we can say the transformers connected in parallel will share the load according to their equivalent impedances in ohms, and this impedance will be inversely proportional to their kVA rating. See, from this equation we can write ZEA is proportional to 1 by IA. So 1 by IA, that is the load current. So if we convert this into VA, that is volt ampere, then we can write this proportional to 1 by kVA load shared. Okay, so that is our condition 2. Okay, now let us consider case 1 where this ZEA and ZEB, that means the leakage impedance of these two transformers, are equal. So what will happen? And also another condition is there that the ratio leakage reactance to resistance ratio are not same. The value ZEA is equal to ZAB EB, but this ratio XEA by REA is not equals to XEB by REA. Reactance to resistance ratio are not same for these two transformers. So according to this relation, if we take tangent of this, then we will have tan inverse X by XEA by REA is not equals to tan inverse XEB by REA, which means phi A is not equals to phi B. That means the power factor angle of transformer A is not equals to power factor angle of transformer B. Now, as per our first assumption, that is equal voltage ratio, this EA and EB both are equal, and since the leakage impedance drops are also equal, so we can write IA ZEA, that means the voltage drops are also equal, therefore the leakage impedances are equal, and which means the currents are equal. So what is the conclusion here? When leakage impedances are equal, though this reactance to resistance ratio are not same, in that case the transformer will share the load equally. Is it clear?
So that should be REB, na?
Oh, this one, yes, REB, correct. That is typing error, sorry. So anyway, so here the conclusion is, for transformers connected in parallel, if the voltage ratio is same and the transformers are having equal impedance, leakage impedances, though the reactance to ratio are not same, they will share the load equally. That means IA equals to IB. Okay, whatever load may be connected across this parallel combination, the load will be equally shared by the two transformers. Okay, so that is the phasor diagram for this condition. You can see IA is the load current of transformer A, IB is the load current of transformer B. Here the phasor power factor angle phi A and phi B are not equal due to this ratio is not equal. This is B, but the voltage drop, that is, for suppose for transformer IA, this resistive drop and this reactive drop, which will give you the total leakage impedance drop, that means the resultant of these two, that is this is V, and the leakage impedance drop, that means for transformer B, that is resistive drop this line and reactive drop this line. Resultant of these two will give you the voltage drop this, which is also V. Okay, so this line is same. From this we can conclude that the current value, this IA and IB, though they will make different angle with this voltage drop V or the terminal voltage capital V, but their magnitude will be same. That means the load sharing will be equal. Okay, So here phi B is greater than phi A. To draw this phasor diagram, we have assumed that phi B is greater than phi A. So depending on that, there will be resistive drop. Two resistive drops are unequal. Similarly, two reactive drops are also unequal, but the total leakage impedance drop will be same. Okay. So the secondary terminal quantities, that is Vi and power factor cos theta 2, are taken to be known. So if we so this is the phasor diagram which we have drawn in our previous slide. That means this one. Okay, so this is the phasor diagram which will appear here, and with it, that means if the reactive drop across transformer A, that means this one, and the reactive drop across transformer B, again this line is added to the terminal voltage V, then we will get the induced EMF across transformer A or B. That is our equation. EA is equal to V plus IA ZEA, which is equal to V plus IB ZEB, and that is equal to also EB. So as per this equation, we can draw this phasor diagram. Now what is the relation with this voltage and current? See, the voltage, terminal voltage, lags the load current by an angle of theta 2, that we have assumed. Okay, so here power factor angle is theta 2, and this load is equally shared by the two transformers. So the current magnitude IA and IB are same, so they will therefore the angle between this IA and IB, which is phi B minus phi A, will be equally divided by this total current I. So the magnitude of IA and IB are same, but they are making different angles with this terminal voltage or this induced EMF EA or EB. Is it clear?
Yes, sir.
That means when the two transformers are having equal induced EMFs and their leakage impedances are equal, then though the reactance to ratio are not equal, they will share the load equally. Okay. So phasor sum of IA and IB will give you the total current I. This I lag the voltage, terminal voltage, or the voltage appears across the load by an angle of theta 2, which is the power factor angle, load power factor angle. And if we add the two voltage drops, that means the leakage impedance drop across either transformer A or transformer B, then we will get the induced EMF across transformer A or B. Now from this phasor diagram, we can see that the power factor angle of transformer A is this angle, and power factor angle of transformer B is this angle. So power factor angle low means higher value of cosine value, and power factor angle higher means lower value of cosine of that angle value, which means in this type of operation, if the leakage impedance to resistance, leakage reactance to resistance ratio are not same, then though the transformer will share the load equally, but one transformer will run with a better power factor and the other transformer will run with a poor power factor. So our third condition was that this X by R ratio must be same. If not, then this thing will happen. Is it clear?
The power factor is better when the value is high.
Angle is lower.
Angle is lower, cosine is higher. Okay, sir.
Cosine is higher. We always want that power factor should be nearer to unity. Okay, so cos 0 is 1. So we always want that this voltage and current must be in same phase, but that practically doesn't happen due to the inductive nature of load. So there we normally the power factor value is 0.8 lagging for any normal inductive load. Most of the loads are inductive in nature, so the power system will have a power factor of 0.8 lagging. That is the normal situation. Okay, but though the power factor of load is 0.8 suppose, but the when this load sharing is done by two transformers having unequal reactance to resistance ratio, then one transformer will run with a better power factor, that means power factor nearer to unity, and the other transformer will run with a poor power factor, that means its power factor will be far away from unity. Okay, so our third condition, that means the X by R ratio must be equal. If that condition is not satisfied, then this will happen. If the leakage impedances are equal, then they will share the load equally, but one transformer will run with a better power factor, another with a poor power factor. Is it clear?
Yes, sir.
Any question here? Okay, so here we can conclude that here ZEA equals to ZEB and IA equals to IB. Therefore, as per equation 6 means this equation, and 7 the next equation, the KVA shared by transformer A and B are equal because this ZEB and ZEA both are equal. So this ratio becomes half 1 by 2. So SA equals to SB. So the total load will be shared equally by the two transformers. The total output KVA proportional to I is reduced because I is the phasor sum of IA and IB and not the arithmetic sum. So what is the meaning of this? See, the total KVA output proportional to I is reduced because I is the phasor sum of IA and IB and not the arithmetic sum. Okay, so total KVA, suppose a load of 5 kVA is connected as across two transformers. Okay, so if the, if the current is suppose 100 ampere, then the current drawn by transformer A and B will not be equal to 50 ampere each because they are not phasor sum. Sorry, they are not arithmetic sum, so they are phasor sum. So they will make some angle with each other and also with some angle with the total current I. Therefore, some other value of current will give you the resultant as 100 ampere, which means this suppose that value is 40 ampere. Now 40 into the terminal voltage will give you some kVA, and sum of those two kVAs will not be equal to this total kVA 5. That means the capacity of transformers, suppose the sum of the total capacity of transformers is 5 kVA, but we will be able to use only suppose 4 kVA. total capacity we cannot use for this kind of situation. Is it clear?
Yes, sir.
So that is another disadvantage if the X by R ratio are not same for all the transformers. So in general, when reactance to resistance ratios are not equal, their full load kVA output is less than the sum of their individual kVA ratings. Okay, so suppose individual kVA ratings is 2.5 and 2.5 each, so total kVA capacity is 5 kVA, but due to this unequal resistance to reactance to resistance ratio, we will be able to use only a part of this 5 kVA, suppose 4 kVA. So that is one kind of loss. Okay. Now case 2. The main assumption remains same, that means equal voltage ratio across the secondaries remains same. Here one of the transformer is having higher leakage impedance than the other, that means the leakage impedances are not equal, but the X by R ratio is same for both the transformer. Okay, so what will happen? Since the X by R ratio is same, therefore power factor angle will be same, phi A equals to phi B. That means the impedance angle of transformer A and transformer B are same. Therefore, we can draw the equivalent, the phasor diagram based on that equation. So here, due to this equal voltage ratio assumption, again we will be having this voltage drops are equal. IA ZEA is equals to IB ZEB is equals to this voltage drop V, small v, and since these impedances are not equal, therefore current sharing will not be equal, that means load sharing of these two transformers will not be equal. So here, since ZEA is greater, so IA will be lesser, so that means the load shared by transformer A will be less than that of transformer B. So here is the phasor diagram. You can see IA and IB are in same phase with the total current I, and the reactive drop, that is, this is the resistive drop, this is the reactive drop, and the total leakage impedance drop is V for both the transformers. They are equal as we have seen. So if this drop is added to terminal voltage V, you will get EA and EB. Okay, so this IA and IB both are making same angle with the voltage, but their magnitudes are not same. Okay, so here what happens, the load sharing is unequal, but as they are, that means the two currents IA IB and the total current I are in same phase, so by adding algebraically IA and IB we will get I. Okay, because they are in same phase and lying, and they are lying along the same line, so simply we can add them, no phasor addition is required. Okay, so by adding IA and IB we will get the total current. Okay, so here we can use one advantage is that here we can use the total capacity of the two transformer, but there is another problem. Let us see. So both the transformers are seen to operate at the same power factor and the total output kVA is increased. Okay, that means the capacity of the two transformers will be properly used. Now see, sum of IA and IB for phi A phi B, the total output kVA is equal to the sum of the kVA ratings of the individual transformer, as I have mentioned. So the kVA supplied by transformer A is EA IA into 10 to the power minus 3, and EB is this, I mean transformer B. So ZEA is greater than ZEB, IA is less than IB. So EAIA, that means the volt ampere of transformer A is less than volt ampere of transformer B. That means the load shared by transformer A is less than load shared by transformer B. Okay. So we can conclude that transformer having greater equivalent leakage impedance shares less kVA, and that having lower equivalent leakage impedance shares greater kVA. Transformer of different kVA ratings can be operated in parallel provided their equivalent leakage impedances in ohms are inversely proportional to their respective kVA ratings. So this point is very important. I have observed that while asking this question that what are the conditions for parallel operation of two single phase transformers, many students said that all the transformers must have equal kVA ratings. That is totally wrong. Okay, so this is not a condition. Transformers with unequal kVA ratings can be operated in parallel provided their equivalent leakage impedances in ohms are inversely proportional to their respective kVA ratings, or per unit leakage impedance based on their kVA rating must be equal. Then only we can operate different transformers with different kVA ratings in parallel. Is it clear?
Yes, sir.
So different leakage impedance, suppose EA is greater than ZEB, but their X by R ratio is same, which means power factor angle is same. So by using that kind of that condition, we can operate different transformers with different kVA ratings. So one transformer will share lesser load and one transformer will share higher load. So accordingly we can design the kVA rating of those transformers. Okay, but if we take equal kVA ratings, suppose 2.5 kVA kVA rating of two transformers, and the load connected is 5 kVA. Okay, so these two transformers will share the load as per this condition. That means one transformer will share lesser load, another transformer will share higher load, though their power factor remains same. Okay, that means it may happen that one transformer is lightly loaded. That means suppose one transformer is loaded with 2 kVA load and the other transformer is heavily loaded, that means overloaded, that means 3. So 2 plus 3, that also makes 5. Okay, that is the problem of this kind of situation. As I have mentioned that there is some other problem. Is it clear?
Yes, sir.
If we have this unequal leakage impedance but equal X by R ratio, then we have to take those transformers with kVA rating as per their leakage impedance value. Okay, that means we have to follow this relation that the kVA loading, kVA is inversely proportional to the impedance, leakage impedance, following this relation. If we do not follow this relation, that means suppose randomly we have taken equal kVA ratings and still they are having different leakage impedance, then this kind of underloading and overloading problem will be there. Okay. So equivalent leakage impedance is inversely proportional to kVA rating of that transformer, or ZEA is proportional to 1 by SAR. This is the rating, that is why it is SAR, and ZEB is proportional to 1 by SBR. Therefore, we can write ZEA by ZEB is equals to SBR by SAR, because they are inversely proportional, and SAR and SBR are the rated kVA of transformers A and B. Okay. But IA ZEA is equals to IB ZEB. So IA by IB equal to SAR by SBR. Sorry. So using this relation, we can find the kVA load sharing of the transformer. So these are ratings of two transformers. This is the load current of transformer A and this is the load current of transformer B. Okay. Any question up to this?
No, sir.
Okay, next is on-load operation with unequal voltage ratios. Okay, so if unequal voltage appears across the two secondaries of the two transformers, then what will happen? So unequal secondary EMFs give rise to circulating current, that we know, and when the load is connected, the transformers share the load current in proportion to their kVA ratings. This also we know, and that depends on their leakage impedances. So the resultant current in any transformer is equal to the phasor sum of circulating current and the load current shared by it. So now some circulating current IC will be there, and so therefore this IC will act as a load to that particular transformer also. So load shared by any particular transformer is the actual load shared, that means actual load current plus the circulating current. Okay. So let the two induced EMFs EA and EB are not equal. So this inequality can be created by making their magnitudes different or making their phase angle difference. So let us consider they are not in phase. So we are assuming that EA is greater than EB. Load current I lagging the terminal voltage V by load power factor angle theta 2, and let us assume that the two transformer share this load equally. So the total current IA is shared by the two transformer, such as IA plus IB equals to I. So this was our equation 1 and this was our equation 2. Now see, if EA and EB are not equal, then what happens? IA is equal to I into ZEB by ZEA plus ZEB, plus this is the circulating current actually. This is the load current shared by transformer A, actual load current, and sum of these two currents will be the load current, total load current of transformer A. So solving these equations, you will get the expression of IA and IB also. You can try it by yourself. So I am writing it directly, and see, this is IC, EA minus IB by ZEA plus ZEB. Therefore this is equation 12, and IB equals to this current minus the circulating current. We have seen that the direction of circulating current in one transformer is same as that of the induced EMF, secondary induced EMF, and the other in other transformer it is opposite to that of induced EMF. So this negative sign appears. Okay. So I into, that means this is the current due to load, and this is the current, this is the circulating current. Okay, so that is the situation when unequal voltage appears across the two secondaries of the two transformers connected in parallel. Is it clear? Anyone having any doubt? Okay, draw the phasor diagram for this kind of situation. That means when circulating current is present. Okay. Now let us solve one numerical example. So here a 500 kVA transformer with 1.5% resistive and 5% reactive drops is connected in parallel with a 1000 kVA transformer with 1% resistive and 4% reactive drops. The secondary voltage of each transformer is 400 volt on load. Determine how they share a load of 500 kVA at a power factor of 0.8 lagging. So first of all, what is the situation? Two transformers are connected in parallel having unequal kVA ratings. Okay, and their resistive drops and reactive drops are also given. So from that you will be able to check whether their reactance to resistance ratio are same or not, their impedances are equal or not, etc. Okay, so how to determine? First of all, determine the per unit leakage impedance. So 1.5% resistive and 5% reactive drop means that will be the per unit impedance of transformer A. So a percentage impedance, so if you divide it by 100 you will get percentage per unit. Okay, so this is the per unit leakage impedance of transformer A, and this is the per unit leakage impedance of transformer B. Okay, now taking 1000 kVA as the common base, so to calculate the per unit leakage impedance of the two transformer we need one common base, because these two transformers are connected in parallel, so they will make one system. So all the calculations has to be done with one common base. So let us consider this 1000 kVA as the common base. So therefore this per unit value, per unit leakage impedance of transformer A with respect to this 1000 kVA common base is equal to this. Initially this per unit value was based on its own rating 500 kVA. Okay, so now we are calculating the per unit leakage impedance for transformer A with respect to 1000 kVA. So first of all, the per unit value is converted with respect to this 1000 kVA base. Then for transformer B, it remains same because it was already calculated with respect to this base. So these are the two per unit impedances with respect to 1000 kVA base. Okay. So total load 500 kVA at 0.8 lagging PF. So cos theta equals to 0.8, theta equals to this. Therefore, this kVA load can be written in complex form like this, in polar form, which will give you one active component and one reactive component. Sorry. Therefore, SA, that means load shared by transformer A, using this equation, load sharing equation, we can find putting the values of all the leakage impedances, per unit leakage impedances. So if we calculate this, we will get this, which is equals to 321.88 minus angle 12.25 degree kVA. So this is the load shared by transformer A, this much kVA. Similarly, using the other formula, or we can directly subtract that SA from S to get SB. So SB equals to this. If you convert this in polar form, you will get this. Okay, so this is the load shared by transformer B. Okay, so now observe load shared by transformer A. How much was that? $322 approximately, which is close to 500, but in case of transformer B, it is only 246, which is far away from 1000. Okay, so that means with this type of resistive and reactive or leakage impedance, we are not able to use the kVA capacity of the two transformers properly. Okay, so if we increase the load, then this 500 kVA transformer will get overloaded to reach the capacity of this transformer B. Is it clear? Any doubt? Hello?
No, sir.
Okay, practice this type of load sharing problem. So note down this problem and try to solve it by yourself. Take a snapshot.
Yes, sir.
Okay, done?
Yes, sir.
Okay, so that's all about single phase transformer. From next class, we will start three phase transformer.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay, just wait. Let me
Thank
take
you,
the
sir.
attendance.